Hi children, good morning. Welcome to class. Children, in the previous class we were discussed about techniques like distillation, crystallizations, and I showed you how to do also. Am I clear? That activities. So the same thing continues now. The remaining parts or the remaining methods like chromatography and sublimation. This both also are remain. So children, I informed you these are the activity based. So this entire lesson depend upon through activity we have to do. When you come back to the school, definitely will make a activity regarding to this lesson and the previous lesson also. That's I made it. Especially this sublimation and chromatography. Children, I want to say about sublimation. So the states are changing into three states. Classification of the states like objects are changing into three states depend upon the temperature, isn't it? So this sublimation is not like the mixture of the copper. Example I am telling, the mixture of the one substance is changing into solid to gaseous form directly. Usually any object has to be changed by solid to liquid, liquid to gases. But this sublimation is a changing direct from solid to gaseous form. Is known as called sublimation. Very simple logic. All the substances are changing, or all the objects are changing from one state to another state, from solid to liquid, liquid to gaseous form. But this is the one, some very few are changing direct from solid to liquid, solid to gaseous form. Is known as called sublimation. The best example copper. See children, sublimation. A solid substance changing directly into vapor when heated without changing into liquid, back to solid by cooling. So it's not changing into liquid, it is changing into solid form again by cooling, isn't it? So if you have the ice, when you cool, it has to come to the gaseous form to liquid and liquid to the solid again if you cool. But this is not like how other materials. This is the sublimation changing from solid to gaseous form. Again if you cool that, gases to solid form only, isn't it? And I will show you this activity also. Okay children, fine. Now let's discuss about chromatography. So this is the one of the best activity we can make in the classroom. I had been lot of the experience with my children when the previous classes in the 6th class, how many were they went up the level of. So really they were enjoyed with chromatography. When we see outside in the atmosphere, we usually see different colors and the common. During a rainfall, we found a rainbow. When you look at that rainbow, you see that colors are different, separating that rainbow to 7 or 8 colors. So the same thing happens in all the colors. For example, black, red, green, or any color you take, all the colors consist or hidden some different colors. So a mixture of the, let me see, a technique for separating a mixture. For example, if I have a black color, if I take a chalk, so whole chalk we have to take. I have taken the whole chalk, and with maybe specs or a pen, you take and just you make a mark here. Just put into the water without disturb that color, which is the mark one, and just to see while observing, when it has to observe this water, slowly these colors are changing, I mean separating one by one, isn't it? So this is the activity definitely will make in the classroom when you come back with individually. Whether this chalk or sometimes what we say tissue paper also we can make, but chalk we can get good result, tissue paper will make quick result. It takes maybe 2 to 5 minutes time to get the result, but this tissue paper minute it takes, and little some clumsy will get in the tissue paper, but whereas this chalk will get very clear crystal, isn't it? So this is the way we can make this chromatography activity in our classroom, and I will show you also how to do. Don't make in your house these activities. What I said that you can do, but this kind of the activities don't make in your house. That you supposed to be do in your classroom, or if your parents are they know well, we can make under their guidelines only, isn't it? Don't unless make creativities. So these are the very important, and this chromatography in our daily life or real life activities, we can make them foreigns or to make the any crime to separating the material things, or dog pads, or this kind of the things we can in a real life applications we can make, isn't it? So this is very important. When you go to higher classes, you can get more knowledge regarding to this chromatography. Am I clear, children? So up to here we completed methods of separation, isn't it? Already I said first hand picking method. Am I clear? Winnowing method. Next decondensation or sedimentation, sieving method, next crystallization, and another one is the distillation, next this sublimation and chromatography. Am I clear? These all the things once you revise and we do this activity in our classroom. Am I clear, children? Have a nice day. Thank you.
Sublimation. If you keep naphthalene balls exposed to air for some days, it is observed that their size gets reduced after some days. This happens due to a phenomenon called sublimation. Normally, solids transformed into liquid on heating, but in sublimation, a solid gets directly transformed to a gas on heating or on exposure to air. In above case, as some mass of the naphthalene balls is converted to a gas, they get reduced in size. There is a simple experiment to study sublimation. Some ammonium chloride is taken in a china dish and a glass funnel is kept inverted on it. A cotton plug is inserted into the funnel and the china dish is slowly heated. It is observed that ammonium chloride on heating gets directly transformed into vapor. Also, the vapors get cooled on the glass surface and are converted into solid form. Thus, we infer that ammonium chloride undergoes sublimation and hence is converted into vapor form directly. Also, the vapors when allowed to cool directly get transformed into solid state.
This video shows an example of a chromatography experiment. The goal of the experiment is to separate the different pigments of ink which are present in a wet erase marker, which we'll see right here. So a vis-a-vis marker is wet erase, which means that the pigments are water soluble. We'll start our experiment by drawing a line with the marker on the chromatography paper. Then what we want to do is insert that chromatography paper into a beaker with a small volume of water in it. We can see that the water will start to rise up the chromatography paper because of capillary action. You'll note this is happening very quickly because this is 16 times speed playback. We can see that the ink, which originally looked black, is starting to separate into different colors. This is because the different pigments have different properties. Some of them are heavier, some are lighter, some are more soluble in water, some are less. Because of these differing properties, all of the different colors are going to travel at different speeds. And by the completion of our experiment, we should see some very nice separation of the different pigment colors. Now, to do analysis of our results, what we're going to want to do is to measure the distance traveled by each pigment. Let's pause here for a moment. So I want to measure the maximum distance traveled by the water and then by each different pigment starting at the line drawn on the paper. To be fair, we should be comparing the distance traveled by the water starting from the same point where the pigment started traveling. So we'll measure all of our distances starting at this point. Looks like the maximum distance traveled by the water reaches about to here, and then we can measure the maximum distance traveled by each of the different pigments. Let's continue our playback. The final part of our analysis will be to calculate an RF value. This is going to be a different calculated number for each different color pigment. For a pigment which travels exactly the same distance traveled by water, which is the solvent or the mobile phase in this experiment, the RF value would calculate to be 1. That's because the distance traveled by the pigment would be the same as the distance traveled by the water. If we had a pigment color which travels half the distance of the water, the RF value for that pigment would be 0.5.